Okay, we are live. Um, so welcome everyone. Uh, Today, in the Topos Institute Colloquium, we are pleased and honored to have Jason Gross, who will be speaking to us about compact proofs, measuring the quality of understanding with a compression-based metric. I'm really excited about this. So Jason, whenever you're ready.
Cool. Thanks for having me here. So we did a really cool project on proofs and mechanistic that has implications for understanding. And I'm going to talk about that here. And by we, I mean this amazing team of researchers. You can think of mechanistic as taking large models and compressing explanations about them. And the byline for this talk is we want to quantify how much we're able to compress explanations using mechanistic understanding, and we're using proof length as the metric. And I want to start by talking about motivation. So why care about mechanistic? There's a variety of reasons. We might want to understand the models better. Mechanistic is like looking at models, or another way of looking at mechanistic is looking at models and looking at what are they doing, how do we understand them. We might want to be able to evaluate models. We might want to be able to control them, make sure that they're doing what we want them to do and not something else. We might want to get formal guarantees about the models that they're doing the thing that we think they're doing. And we might also want to be able to distill models, be like, we have this trained model that does a variety of tasks. How do we get out a smaller, cheaper model that does only the particular tasks that we care about? And then as far as metrics on mechanistic, there's standard reasons that you might want metrics for something. If you can measure it, you can optimize for it. And relatedly, you can automate it. That is, if we got AGI tomorrow, I don't think we could build a trustworthy automated pipeline for discovering mechanistic explanations in a way that we could reliably use. And finally, if we have a sufficiently rigorous metric, it could help us get guarantees. And here we're using formal proofs as our metric on mechanistic. And so we get the highest standard of trustworthiness. In mechanistic, you have a claim about how the model behaves. And the model's empirical behavior may diverge from the claim a little bit, but if your understanding of the model is any good, the divergence won't be that big. They'll be pretty close. And to prove that, this is your theorem statement. And to prove this, you compute the worst case divergence between the claim and the true behavior. So formally, we can write out that the expectation of pairs of data points and labels drawn from some distribution of some function f, which measures the divergence between the two behaviors, on the label y, which is the behavioral claim, and m of x, the model's true behavior on the data point x. You want to say that the divergence is, so depending on how you measure divergence, you might want to say it's less than or equal to some bound b. If f is, for example, log loss, if f is something like accuracy, you'd want to say it's greater than or equal to some bound b. And you could just negate the f. And so, or like you could negate the f and the b and capture it only with greater than equal to. And so getting the proof is the sort of sound approximation to what the actual expectation function is, a sound way of computing b. And the length of the proof is just the cost of running whatever computation you have that is computing b. The baseline approach to computing these bounds is just to run model inference to bound accuracy, to do all the matmols and write them down. To get a good accuracy for any fixed data distribution, we have linearly scaling costs. So at one extreme, we have the trivial proof, where we run inference on no data points whatsoever, and we say the model has accuracy greater than or equal to 0%. On the other extreme, we have the brute force proof, where you run the model on literally every data point that you care about, And you get to say that the model has accuracy, whatever its true accuracy is. And we can linearly increase or decrease the cost to get any bound in between these. The hypothesis that we have is that understanding of the structure can help recover bound tightness, can give us a Pareto frontier that is better than this linear baseline, where we get better bounds more cheaply. We tested this hypothesis on a toy model, very toy model, by producing proofs that incorporate varying degrees of mechanistic information about the model. And briefly, I'll say that in the brute force proof, we don't peek into the internals at all. The cubic proofs sort of gerrymander the input set and use relationships between the different paths through the network. And the subcubic proofs use information about the actual paths and how they're computed. We find, as hoped for, that more mechanistic understanding allows computing better error bounds cheaply. Notice, however, that going from right to left adds mechanistic understanding, but worsens the bound. That is, proofs with more mechanistic understanding have bounds that are much better than the linear baseline, but still much worse than longer proofs. The puzzle here is, why does more structure not always mean a better bound? And our concrete metric reveals why this is the case, why mechanistic understanding isn't sufficient to compute excellent bounds, perfect bounds cheaply, because compression requires structure. And when we've explained all of the structure that we can find, we're left with apparently incompressible structureless noise and quickly compounding errors. So the toy case that you see on the screen here for this is for the QK circuit, which, if you don't know what that means, that's fine. And if you do, great. Once you've extracted all the structure in the circuit that decides how the transformer is paying attention to which tokens, you're left with these four matrices that you multiply together to get the error term based on our understanding of the structure. So it's like there's some structure in the QK matrix, and then this is what remains that we haven't explained. And how big the error term is depends on the largest difference between two elements in the same row in this matrix. And in fact, that number is 1.8, and you should think of this as a log ratio between attentions. So if you have a difference of 1.8 between two things, this means that you pay about e squared times more attention to one of them than the other. And this is the error term. And the scale of numbers in the structured part goes from something like -80 to 80. So something like e to the 100 or e to the 160 is the largest difference in attention that you would see. The structure in terms of how the entries are ordered in the matrix is not that big. If you just look at twice the maximum absolute value, you get 2. So it doesn't matter what row you're looking at. If you want something that is cheaper than multiplying all the matrices out, you can, there's a trick that I found where basically you compute the difference in rows in the matrix on the right, and then you multiply that by some things on the left, and you move some absolute values around. So matrix multiplication takes the product of the three dimensions to compute. So here it's dvocab squared times dmodel. And dmodel is generally smaller than dvocab. So if you go down to dvocab times dmodel squared, our bound is a little bit less than 6, which is worse, but still usable. If you want to go down to something that is linear in the number of parameters that you have, you end up with a bound of 97, which is not quite vacuous, but is still pretty terrible. It gives us almost nothing. And the question here is, how do we deal with the fact that there's not much happening, but we don't know how to prove that there's not much happening? And I want to throw another sort of brain teaser in for the same sort of puzzle, perhaps a simpler one that didn't come up exactly in our model, which is if you have a collection of vectors, I forgot to add a slide for this one, but if you have a collection of vectors in high dimensional space with plus and minus 1 in all the entries, and you choose them randomly, they're almost always almost orthogonal. And the way to think about this is that if the locations of the pluses and the minuses are independent across all the vectors, the dot product between any two of them will, so each one will roughly have half pluses and half minuses on average. And the dot product between any two of them will have uncorrelated locations where the signs are the same and the signs are different. And so on average, the pluses and the minuses will cancel out. And so on average, you'll get approximately 0 dot product between any two of them. However, if you want to actually prove that a particular collection of random vectors in high dimensions is nearly orthogonal, I have yet to find any way that is cheaper than just taking all the pairwise dot products. So this is something that's quadratic in the dimension, quadratic in the, or sorry, it's number of vectors squared times dimension, so cubic in the dimension, as opposed to just quadratic in the dimension, if the dimension and the number of vectors is about the same. So how do we deal with these sort of unstructured, sorry, I will get to how we deal with these unstructured error terms in a moment. First, I want to talk about current applications of this approach. So there's one project that we're currently wrapping up where we compress the MLPs, the nonlinearities in the network, which as far as I am aware is the first time that mechainterp has managed to actually compress the MLPs. And in the modular addition models, it seems like the thing the MLP is doing is numerical integration. And we have more evidence than just seems like. What I mean is that by using the hypothesis that it's doing numerical integration, we can compress the proof of the MLP down to time that is linear in the parameter count, which I think is moderately strong evidence that in fact it's doing something like numerical integration. Although the bound is not super tight, and the bound is not tight because we don't really know how it's laying out the boxes. Like each neuron is responsible for one box, but the box widths are non-uniform and the centers of the boxes don't line up with the point at which the neurons evaluate the curve always. And so there's these error terms that we're not sure how to bound concretely. But here again, we see I would claim is a win for the compact proofs metric, because the thing that we're blocked on making the bound better with is our lack of understanding of how the network is actually doing numerical integration. Another application is as giving a ground truth for comparing different mechainterp approaches. Here there were two different interpretations of the same network, where the first one was in terms of irreducible representations. And then a second paper came along and was like, seems like it's not irreducible representation, seems like it's cosets, and they gave some evidence for that. And then using the proofs approach to really drill down into the details of what's happening, the group found a detailed explanation of what exactly is going on in the MLP in terms of irreducible representations that explains both the irreducible representation results and the cosets results in a way that allows getting a non-vacuous proof that's cheaper to compute than brute force, which neither of the original explanations alone permits. And finally, this is a sort of software application. The approach suggests how to do optimization targets for representation search. Here, I mean SAEs, sparse autoencoders, where for any technique that you're using in mechainterp, you can ask what does this have to say about proofs? If we're trying to compress the explanation, trying to compress the proof, what does this technique have to say about proofs? And that might suggest, if you have arbitrary choices to make in how you're applying that technique, this might suggest how to choose some of those parameters, how to use So in SAEs in particular, they seem to give you case analysis and proofs. And so unless you can prove that the bits of the network that you care about distribute additively over your features, this suggests that you want a multiplicative or combinatorial penalty for sparsity in training sparse autoencoders rather than an additive penalty.
Well, Jason, I have a quick question.
Yes.
So when you talk about compressing neural networks, you mean distilling them into a smaller neural network, network with a smaller architecture?
Yeah, that's a great question. So distilling them into a smaller neural network with a smaller architecture will allow you to do the sort of compression that I talk about. But what I mean, where is it? What I mean is compressing the sort of literal proof that by default is the transcription of all the computations on all of the data points that you care about. So if you can prove that your compressed network evaluates to the same thing within some error term of the larger network, then this allows you to compress this transcript because you only have to run your smaller network on all the data points that you care about. But you can also do other things. For example, you can say there's this compressed network for this chunk of data points. There's this other compressed network for this other chunk of data points. And so you can do a sort of disjoint compression between them. And you can potentially even do more complicated things for factoring, for example, with the numerical integration.
I see. So you're compressing the proofs by compressing the networks. To some
Yes.
extent. Okay.
And you can also look at compressing the proofs without compressing the networks.
Okay.
In this approach, I'm using compressing the proofs as the ground truth of what we're targeting. And whether we get compressed networks out of that is a question of how good the approach is for like whether or not we can apply the approach to get that application.
Okay. Thank you so much.
Yeah, great question. Okay, so the question that I want to end with is, what is the research agenda for scaling compact proofs? What are the open problems if we want to apply this to getting guarantees about real frontier models, for example, about actual AI and not toy models, the one that I was showing the pictures for before, like one layer attention-only transformers? What do we need to do? So the first thing we need to do is we need to fix this noise problem. We need to fix the compounding error terms. And there's 3 approaches that I am optimistic about for that. One of them is some work in progress by the group on fine-tuning. The computation of the bounds in the theorem statement is differentiable, or is often differentiable. It's just a program, a computation. So you can throw that into the loss function and fine-tune on it. And this should make the bound better. And it may also make the behavior of the network better, the actual performance. And we have preliminary results that are reasons for optimism. The real question, of course, is can you do this without destroying its performance on other tasks? Another promising approach is arc theory's heuristic arguments, where you are trying to find a relaxation of proofs that is still rigorous, but lets you make average case claims instead of worst case claims, where you get to make arguments like, well, if all the entries are independent, then the pluses and minuses cancel out on average and have that go through. And another approach is, once we've explained the structure with proofs, taking our structureless remainders, maybe having some measure of how structured or structureless they are, and doing sampling on those and seeing what sort of bounds, maybe like pack bounds, we get out of that. The next problem that needs to be fixed is that the proofs approach requires addressing everything in the network, including the things that don't happen. And if you do this pathwise, you get an exponential in the number of layers. And you can see this already in a toy model of induction heads, where you have something like 3 or 4 paths through the model that actually matter. And something like, I should have computed the numbers, but something on the order of like 16 paths through the model that don't matter whatsoever, or like shouldn't matter, where you're just trying to say, let me upper bound this so I get an error term on this. And the hope that I have for this is that if you can do a mixed path and layer-wise decomposition where you do a path decomposition for the structureful parts, and then you treat the apparently unstructured parts layer-wise, and hopefully this allows us to not be exponential in the number of layers. This is still to do, still future work, as is everything, or most of the things on this slide. If we want to make this a metric for being able to fully automate mechanistic, we need to also be able to auto-formalize the proofs so that we're not doing them by bound. In particular, these are the proofs that the computation of the bound is sound, that it always gives a valid lower bound on the performance. And here we want something like alpha proof. And finally, we want to do automatic interpretation. I think there are plenty of people working on this. And step 3, profit. Thank you.
Okay, thank you, Jason. I guess yeah, we have a shorter talk today, but this gives us a lot of time for questions. So first, let's thank Jason for his talk.
Thank you. And I want to mention I have a bunch of, so I made these slides by combining some previous presentations, and I have a bunch of extra slides that delve more into the details, but it felt like giving a like more coherent story, had them set to the side. So if you're like, I want to just double click on this, it's entirely possible that you'll be like, tell me more about this. And I'll be like, here are my slides that tell you more about that.
I do like the style of having more questions, and then you jumping into detail on another set of slides. So let me just remind everyone how we do questions in this colloquium. You can either raise your hand and then I will call on you to unmute yourself and you can ask your question, or you could type your question in the meeting chat and I'll be happy to ask that question on behalf of you. Okay, so let me know if anyone has any questions. So I think some of us know about David's program, which is looking at Steve Goddard AI, his program in ARIA. I see that the bounds that you're trying to prove is very similar to the kinds of bounds that he's looking at his program. Is there any connection? Can you say something about that?
Yeah, so the work was pursued independently. My understanding is that a lot of the bounds that he's looking at are, in some sense, the next level up, where you have your model as part of a larger system and you want to prove some property of its like stream of outputs, or it's like behavior as part of that system. And I imagine from the little that I've chatted with people that he's working with that currently they're looking at much simpler models where it's very easy to say what a sort of individual iteration does, or to compute it by brute force, and looking at what happens when you iterate this and what kind of structure arises. And I think for the models that are more complicated, multiple layers, it'll be non-trivial to get bounds on single iteration even. And so you'll need to do this sort of proof that I'm looking at here to get what is the like functional behavior on each iteration. And then once you have a compact description of what that behavior is on each individual forward pass, you want to assemble that into some sort of larger structure of what happens when you run chain of thought or something like that.
Hmm. Yeah, I do like the approach that you have here, which is that you are instead of just trying to prove directly about uh bounds on the behavior of the large models, you're looking at compressing the models, distilling the models, looking at smaller subparts, analyzing the smaller subparts. I think that's to me, that's quite novel. Like I've really not seen uh I've seen work on distillation, but never seen distilled models being used this way before. And it kind of speaks to me of a it you know I think in trying to uh put bounds or put uh prove certain safety constraints on AI systems. It seems like there's a spectrum of things that you can do. On one end of the spectrum, you could be taking the actual model, the entire model, and then saying that we are not going to give a response that is anywhere close to this bad region over here. Or on the other end of the spectrum, you could say, I don't care what the AI system is doing. All I care is that the outputs, for instance, like the kinds of programs that it writes or the kinds of decisions that it makes would not violate some very specific formal symbolic constraints. And here it seems like the method you're talking about is somewhere, it to me it feels like it's somewhere in the middle where you don't have the AI system writing formal programs like traditional symbolic programs, but yet it's kind of like writing a program. I think of the distilled model as some kind of a program of its own, and that these programs are easier to study or give proofs about than the actual full model. But at the same time, it has more flexibility than the formal symbolic programs, traditional programs that was on the other end of the spectrum. Do you think that this is a way
Yeah,
to think about what's going on, or maybe
I
there's a
think
better
that
way to
is,
think about this?
yeah, I think that especially aligns with the fine tuning part that we're working on, where it looks like if you have some partial understanding, where you're like, oh, these are the important structures, you can then fine tune the model against your partial understanding, and this may make it more amenable to further interpretation. Where like I've sort of somewhat distilled the model, but not fully. I know that only addresses a small part of what you said, but I think uh, broadly I'm on board with the things you said.
Thanks. Yeah. Any questions from the audience? Questions in the chat? So I think this is great. What we're gonna
Hey,
do is we are going to Jason, yes?
yeah. So the to give options for what there are things to double click on, since we have since we have so much time.
We do, yes.
I have slides on more details about the particular model that we studied and what the proofs look like, what sort of interpretations went into those proofs. I have more details on the where was it? Let me jump slides.
Hmm.
I have more details on the a little bit more details on the numerical integration model, and a little bit more details on the investigation that I did with SAEs. I don't have any slides about the groups approach currently. If any of those appeal, I'm happy to go into them. If not, I'm also happy to do whatever you were about to suggest.
Yeah, I personally I'm very curious about how you would write proofs about transformer hits, like attention hits in the transformers. Like it sounds like it would be very hard when you have recurrent structures like that. Do you have any material on that?
Uh, yeah,
Uh,
so let me say a couple words about it. The so the models that we've been studying so far are all they're not all, mostly one layer models. Induction heads is a two-layer model. Um, these are all transformers, not recurrent, which I think is a different sort of problem.
Mhm.
In the transformer architecture, you can do this path decomposition where you look at basically every different way to compose the matrices through the model, and you treat each one separately. And then you're like, oh, this path does this thing, or these combination of paths do this thing. This group of neurons is doing this numerical integral. This group of neurons is doing this other thing. And then you leave over the paths that are just error terms.
Mm.
Where like for the, okay, so diving into the details a little bit, the model that we actually looked at is it's trained to take the maximum of k numbers, k one-hot encoded numbers, and just predict one-hot which of them is the largest. And this is a tiny model. It has something like 10,000, 12,000 parameters. And we read off only the final logic position. And empirically or concretely, for most of the investigation, we studied max of 4 numbers because 4 is the largest thing at this vocab size where you can feasibly do brute force. And I wanted to be able to compare the brute force approach. But we also looked at, does the proof methodology scale to k equals 5, 10, 20, where doing brute force is something like comparable to training ChatGPT or something. And what the theorem looks like concretely, so this is the brute force theorem, where here we're measuring accuracy. We're saying the expectation of, let's find the argmax of the final position of the model's output. What fraction of the time does it equal the true maximum of the sequence? Empirically, for the model that we trained, it was about 99.7% of the time. And we define a computation that computes this bound. In this case, the computation is just running the model on every single input sequence. And then you can prove, you split your proof into 2 parts. One of them is that this computation produces a valid bound. And here, this just goes roughly by definition. Here, you just want to say this Python code accurately computes this expectation. Though for other proofs, it will be a more complicated proof. In the paper we have, there are proofs that use are like a dozen pages or so of LaTeX. And then the other part of the proof, and this is the part that dominates the length, is that this particular computation run on some particular model equals this particular number. And this part is so long because if you actually want to prove this, you need to write out every operation that happens. So you need to write out all the weights and all the data points and sort of run the inference pass with pen and paper on every single data point. And because that is so long, it's almost certainly going to dwarf anything you could write down by hand in LaTeX. And so for most of the approach, we're just looking at what is the asymptotic running time of this computation. And if you want to be fully formal, like if you want to prove this in Lean, you actually need 2 more components to make a proof. One of them is you need to show that you need to find the difference between running the computation on real numbers and on floating point numbers, and establish that these aren't too different. And then you also need to establish a bound on the difference between running your model on real numbers and on floating point numbers, and establish that these aren't too different. And my hope is that these are the 2 parts that I haven't put any effort into actually doing. But my hope is that the existing epsilon ball robustness style proofs, where you set epsilon to be the unit of least precision for float, you're like, what's the smallest amount I can increment float? Let me just look at that size epsilon balls, these tiny, tiny epsilon balls around the points, and show that they don't grow too large. And as long as your transformer isn't too big, that should hopefully be the case. And so I'm hopeful that it's mostly just an engineering challenge to get the other 2 parts of the proof. So coming back to your question about recurrence, or about like I think it was about recurrence.
Mhm.
I think there you get something that is more like looping as a primitive. So there's two options there. Either you can unroll the whole loop, uh, or you can say, I have a loop primitive. And the standard way of proving things about loops is with loop invariance, where you're like, okay, I need to establish some function on what the single pass does with some error term. And then you'll need tiny, tiny error terms because the error term is going to blow up quickly as you increase the number of iterations. And so you need to have some argument that says the error term is really suppressed hard by the actual computation that you're looking at. Or you can fine-tune the model and drive the error term to zero potentially.
Right. That makes sense. Yeah, that's a really good strategy. Yeah, I think you answered one of my questions just now, which was you have this computation here, which I assume seems to be done in C or some other language, definitely not Lean. And
Yeah,
then
we've
you
we've
have
been
this
doing it in
proof
Python.
in Python, and then you have to prove this Python computation uh, produces a number which could be trusted by Lean, and that seems to be hard, uh, at least in from what I understand so far about Lean. But yeah, so you just said that you have to prove this equivalence between, well, not equivalence, but some kind of um
Bound.
bound between the use of floating numbers and floating point numbers and real numbers.
Yeah, so the way it would look to do this into Lean is that the programs are not so complicated that you need to deal with nasty semantics of Python. And so you would just want to translate the computations directly into Lean. And if Lean doesn't already have it, you'd want to augment Lean with some sort of like optimized floating point executor so that it could run. You'd want to basically be able to import the weights of your neural net into Lean, and then run the neural net directly in Lean, and hopefully have it run as fast as it does on PyTorch.
Mm.
And so this is a whole other performance engineering problem if you want like full guarantees. But then once you do this, you can run both the computation and the neural net in Lean, and like do the whole proof in Lean with however Lean would do floating points and however Lean would do reals. And I did this for the brute force approach in Calc and discovered that Calc is about 30,000 times slower than PyTorch, even when using primitive.
30,000.
Yeah, I think most of that is because Calc's version of loops are recursive and deal with closures. And so every time there's a loop, it's juggling a bunch of closures. And this is probably pretty slow.
Yeah, I thought that was funny because Python is already known to be quite slow compared to, say, C. So we
Yeah,
have
well,
this.
but PyTorch is written in C. So
Oh,
when you're
that's
doing
right.
matrix operations, you're batching them, most of it is
That's
happening
true.
fast.
Yeah. So I thought this was a very helpful example where you went through the details, and comment from Janet in the chat is that we would seeing more detailed examples would be very helpful. Um, Perhaps so
Yeah,
I
so
assume this is the one on SAEs. Maybe you could
um
pick another example to
so
go through in detail.
I think that came from before I presented this example, that comment. Um I think before I talk about SAEs, I'm inclined to give the uh what it looks like when you actually use some understanding, like how you modify the computation. So and then I can go on to what it says about SAEs, because the SAEs we haven't done any proofs with. The SAEs are just like using this as sort of inspiration.
Yeah, this will be good. That's a good plan.
Yeah, so great. Okay, so the way the model works, you see the architecture of the model here on the screen, where there's an embed. There's the two parts of the attention circuit. One of them is QK for query and key. The other is OV for output and value, or value and output. And the QK part, can you see my mouse pointer?
Yeah, I can see it move.
Great. Okay. So this part is the QK, and it attends more to bigger tokens. So this is the query side of the matrix, this is the key side of the matrix, is roughly independent of query. It just pays more attention to bigger tokens. And then this matrix, for larger numbers at least, is larger on the diagonal than off. And what this means is that it copies whatever number it's paying attention to and says, I think it's the number that's being paid attention to more than it is any other number. And then there's a direct path in the transformer that we claim does roughly nothing. And we also claim that the positional embedding does roughly nothing. And in the actual paper, this is where you see that I had a bunch of other slides from previous presentations. In the actual paper, we had, I think, 102 different proof strategies. This comes from a combinatorial explosion, roughly, where we have a few different choices about how to treat the error terms and structure, and we just try all of them, going from pretty expensive brute force computation all the way down to something that is linear in the parameters for how it treats the attention circuit. And we could, in theory, nothing is stopping us, I think, from going down to being linear in the parameters in the counting scheme. The main obstacle that we have to getting, I think, I haven't actually run the numbers on going down and counting, but I am nearly certain that we'll get something non-vacuous, although it might be much worse than 30%. The thing that's stopping us from getting all the way down to a proof that's linear in the parameter count, which is sort of the like gold standard, the thing that you want for getting an explanation, is that this copying matrix is a product of two matrices. Its rank is lower than its sides. And multiplying out those matrices costs some time. And the random vectors problem that I described before, we don't know how to establish in time linear in the parameter count that this matrix is higher on the diagonal than off, even though it's just the product of two matrices. But if we could do that and get reasonable error bounds, then we'd be basically at a linear size proof of the model. So the first proof that we go down from brute force is what I've been calling a cubic proof, because it's cubic in the vocabulary size. The k-squared term here, k is the context length, max of k. The having it be k-squared is not essential. It's just convenient to getting good bounds. The only insight that we need for this computation, for using this interpretation, is that there's a single token we want to be paying attention to, which is the max token. That is, we can treat all of the other tokens, other than the max, as error terms. And the way that we do this proof, so the way then that we do the computation is that we say how much more are we paying to the maximum than other things, how much better are we at copying the maximum than other things, how much error could be introduced by paying to other things, and how much error could be introduced by whatever we're computing when we're paying attention to these other things. And the trick that we use to not have to evaluate this on all sequences is what I've been calling convexity of softmax, where you can consider only the pure, what I'm calling pure sequences, where if you, for each pair of, this captures what I just said, that for each max token and non-max token, you're like, how bad is it to pay attention to the non-max token, and how much attention do you end up paying the non-max token? And then you can sort them. You can sort of sort them by a combined score. And then this is the convexity of softmax part, which is that if the model succeeds when your only non-max non-query tokens are some particular token, it will also succeed when the tokens are all better than that token. So another way of thinking about this is that if it succeeds when you have a particular max, a particular query, and A, and it also succeeds when you have a particular max, a particular query, and B, then it'll also succeed on any combination of A and B in the non-max, non-query slots. And this is modulo some handling of positional encodings. This lets us run essentially on only devocap cubed sequences instead of devocap to the fourth. And the details of this are like 10-ish pages of LaTeX in the appendices. And to implement this in PyTorch, the code gets much longer. This is the cubic proof in Python, or the cubic computation. And then this is the thing that we need to prove is correct. So generally what you see is the more detailed your understanding is, the longer the code gets, but the faster it runs. You're sort of trading off time. You're like moving more details into the proof that your computation is always sound in order to get the transcript of running your computation to be shorter. And I guess briefly, I'll say that the like next level of interpretation that you would use in a proof is that because where you're paying attention is monotonic, it dominates the OV circuit. That is, if you're really close, if two tokens are really close, then you're paying similar attention to them, and what OV is doing actually matters. But if they're far enough away, then you're paying less than 1% attention to the wrong token, and basically no matter what OV is doing, the token that you're not paying attention to doesn't matter. And this tells us sort of how to shrink the counting of our proof. And the next level of interpretation, this is where the error term matrices come from, is that the QK attention score is essentially rank 1. What I mean by that is that if you take the SVD of this, the first singular value is 7,000 something, and the next singular value is something like 16. And so you can effectively approximate this as a rank 1 matrix. And so you take the rank 1 structure and run the computation on the data points that you care about with that rank 1 structure. And then you have to treat the error term, and the error term, that's what the previous slide with the four matrices of error term is basically when you subtract off the first two singular components from each of the matrices. What you're left with in this matrix is that error matrix. And yeah, I can say a bit about SAEs, but maybe I will pause to see what there's interest in right now.
There's no any feedback, direction that people like to take this discussion in. I think it's a good idea to talk about the SAEs. I'm interested in that.
Cool. I don't want to get your hopes up too much. I haven't like the investigation. I spent, I don't know, half an hour on the investigation, whereas this I've poured many hours into. So
I would just say, like, in my head, I'm thinking that here you're taking a specific model that has been trained, and then you're proving certain bounds on it. But of course, as we change the training data set, the model is going to change. But what you have is a procedure that can semi-automatically compute those bounds, no matter what training data goes into the model. And so I think it's interesting. Yeah, I'm not sure what you're going to talk about for the SAEs, but if you hear, it seems like you're going to be looking at features which have been learned by the model.
Yeah, I think actually the modular addition might be a more interesting model to talk about for this. So, and I don't have full slides. So
I guess just to wrap up the question that I had, which was the work that you the computation that you showed so far, it's computing certain bounds on the model regardless of the kinds of features that it's learned. And in many kinds of AI, in many kinds of applications, we actually care, say that there are certain features that have been learned by the model, and then how those features are being used, or how good are predictions on those features and things like that. Is this something that you're
Yeah, so one thing that I didn't note here is that you can have a proof strategy that's parameterized over some discovery. And we actually do that in the subcubic proofs, where I said we pull out the first two singular values of each of the matrices, but nothing in the proof uses the fact that it's the first two singular values. And so you can parameterize, we essentially parameterize the proof over the directions that we care about pulling out. And this looks a little bit like a feature where you're like, please tell me what the size direction is, what the key direction is. Please tell me what the query direction is. This is roughly constant. And then the proof, and so you can have different directions for different models, as long as in all of them, the attention score, the QK matrix is roughly rank 1.
right?
And yeah, so, and you can imagine doing the same sort of thing for larger models where you're like, here's the way that roughly the way that I think it's combining features. Maybe I parameterize it over some method of what the features are doing, over some description of what the features are, how they align with the network.
I see. Yeah, makes sense.
And I think the modular arithmetic model is a great example of this sort of thing. So roughly, you don't need to understand everything on the screen, but the thing to know is that the modular arithmetic models compute the sum of two one-hot encoded input numbers modulo some fixed number. And the way they compute it is with trigonometric functions, with sines and cosines. And depending on how you set up the architecture, you might get two different algorithms. And I guess I copy-pasted that token wrong. So let me, where is it? So the integral that's being computed by the network, so this is the linear layer after the ReLU, assigns to each neuron one box under the curve. And then you compute ReLU of the function evaluated at that point times cosine of 2 phi, where phi is also our offset here. And then you multiply by the box width, which is different for each neuron. And then you add them all up. And so you can imagine in a sort of infinite width limit, this approximates an integral. And one thing that you can do here that seems to be somewhat more general than just this model. So first of all, you could have an integral not just in the modular addition model. And I've spent a little bit of time, but not that much time, looking for integrals in other models. And you could imagine a sort of proof technique that is just the integral part parameterized over what you're integrating and how you're doing it. The other thing is that the way that this integral, so the way that the output works on this is that you end up with something that is largest when a plus b equals c. So you take cosine of some frequency times a plus b minus c. And there's a trick that you can use to get that, which is that because the integral is 2 pi periodic, you can do a change of variables where you move the a plus b into the phi, and it disappears from underneath the ReLU. There's this magic that happens that you do this re-indexing or the shifting, and because you're periodic, the dependency of the output on the input you're looking at disappears from the neuron pre-activations and reappears in the weights that you're assigning to each neuron. And you're left with some variation on an axis of the input that doesn't matter for the output. In this case, they'll vary in scale by a minus b, but they won't depend on a plus b. And then you can move this sort of output dependence completely outside the integral. And so you're left with this neuron activation and sum that is basically just computing some relatively arbitrary scaling constant. And you've sort of moved the interesting dependence one layer up. And so this might turn into some sort of technique to look at how networks deal with nonlinearities. Maybe they exploit some sort of symmetry that allows the like math to move the dependence from the input to the output when you like stare at it through the right lens, and then you get a redundancy, and then you can like keep shoving your output through the network potentially. To speak briefly, so this is why I said I think that this is a good example for like how it might generalize. The SAE thing that I had to say. So one of the problems with SAEs is the sparsity penalty, how do we pick the right sparsity penalty? How do we train them? How do we evaluate them? Are the features that we get out any good? Are the features, if the features are bad, is it because the network is using alien features, or is it because we don't, or because we like trained it wrong and we got something that isn't the features? Right now, most of this is done just by manual inspection. But the compact proofs approach suggests that you can use compact proofs or compactness of proof as a metric on the SAE. Or like, well, the question we need to ask for how much understanding is there in the features is how much do they let you compress the computation of the model on all the data points that you care about. And the other thing, this is what I said before about SAEs get case analysis structure. Maybe we should look at something that is a combinatorial-like structure. I spent half an hour investigating this on the most toy models. This is toy models of superposition, basically, with SAEs. I took the initial investigation from Arena. And here is the standard L1 penalty. Notice that it finds duplicate features because L1 doesn't care if you have two identical features of half the size or one feature of full size. Whereas the product-like or combinatorial-like penalty seems to give more closely matching features from the beginning. But again, this is initial investigation. Haven't done that much work on it.
Oh, very cool. Very cool. Yeah, I think we're at about that time right now, and I really enjoyed going through some detailed examples. I think it really goes to show like you know, the general applicability of mechanistic, the kinds of strategies that you can do to gain better understanding or gain proofs of the behavior of neural networks. I think this is a very interesting field that's growing right now. So will you be able to share some of the slides, especially for not just the main talk that you gave, but perhaps some of these detailed examples that people could look at?
I'll delete the slides that I didn't get to or that seem irrelevant, and we'll be sharing all the slides.
Thank you so much, and we will post that on our Colloquium website for anyone who's interested. And please also, reach out to Jason and ask him about his work. I think this is something that we need more eyes looking at, trying to understand and improve things about the behavior of AI models that we have. So last thanks, Jason, again. Thank you so much. It's been a very interesting talk into seeing how proofs can interact with our AI models. I think this is absolutely fascinating what you're doing here. So
thanks so much for having me.
I'm gonna end the YouTube live stream now, and we will head back to the Zoom room. Hey,